For future reference, when I say probability of a sample, I mean the probability of getting that sample or one less likely. Imagine a grid where each square represents a sample of the larger population that is the grid. Let's say each of these samples is part of a normal sampling distribution, meaning that samples with a 0.5 probability happen about 50% of the time, samples with a 0.1 probability happen about 10% of the time, etc. A way to simulate this grid would be to generate random decimals from 0 to 1 for each square. This simulation would mimic the random sampling distribution we would expect to see in the grid, because random numbers under 0.5 and 0.1 should occur in about 50% and 10% of the population as well. Samples of people work the same way. Let's say you're measuring cancer and sampling people by squares on a grid. If there's no extraneous location-related cause of cancer, then regardless of the number of people in the sample, you would expect that any statistics test run on a sample square that determines a 0.5 sample probability to happen about 50% of the time. But forget that connection for now, and let's go back to thinking of the samples as random numbers from 0 to 1. Let's say I search this grid and find a square in this grid that is really unlikely to occur. Its value is 0.001 or something, not really important. If there are only 4 squares in the whole grid, I might think something caused the sample to be off. But if there are 4,000 squares in the grid, it's not that suspicious, so I can't really claim that something messed with its probability based solely on the sample probability. In order to claim that something messed with the probability of the sample, I have to find the probability of getting the sample given the size of the whole population. I can find that probability with the following equation. This equation gives a probability that, out of all the ways of sampling the population grid, which is the number of squares in the grid, none of them are as unlikely as the sample that I picked. Thus, subtracting the previous equation from 1 represents the likelihood of obtaining at least one such unlikely sample in the population grid. If I find that one or more of this type of sample should only occur in about 2% of random population grids, maybe then I can claim that something changes probability, because it wouldn't normally be found in a random grid of this size. Now what if instead of taking one square I take 4 squares in a square block shape and ask the same question? What is the probability of getting these 4 sample squares or something even less likely? Because there is more than one sample in this 2x2 block, it becomes necessary to define what is less likely. The definition of less likely I'm using is as follows. Find the product of the 4 squares, that is, multiply their probabilities. If one block of 4 has a lower product than another block of 4, then I qualify that block as being less likely. If we're going to try to use the same equation as before to answer this new problem, it would seem that we just found the probability of obtaining the sample. It's just the product of those 4 squares, right? Well, let's say the product of the sample is 0.0625, equivalent to all 4 samples having a 0.5 probability of occurring. Finding the product of the samples gives the probability of getting less than 0.5 for all 4 of any random sample of 4 squares. But there are other ways of getting a 0.0625 product that include numbers over 0.5. So assuming that all 4 samples have to have a probability of less than 0.5 is incorrect. Thus, the probability of getting 4 numbers that multiply to 0.0625 is not 0.0625, but higher, because there are more options that 0.5 to the 4th does not cover. There is a formula, backed by simulations and rudimentary calculus, for determining the probability of obtaining 4 random numbers that multiply to any given number or less, but there's no need to discuss that formula here and now. All that we need in order to use our equation is the probability of getting our 4 sample squares or something more unlikely, as well as the number of ways of sampling the population grid. The aforementioned formula obtains the probability of getting 4 random squares with a given product or lower, so now all we need is the number of ways of taking a 2x2 4-square sample out of a certain area. Lucky for us, in our thought experiment, we're using a large square-shaped grid, meaning the number of ways of sampling 2x2 squares is equal to the number of squares and length of the grid minus 1 squared. Now that we have both the variables we need, we can solve the equation by taking the product of our 4 samples, finding the probability of getting those 4 or something more unlikely with our formula, subtracting that from 1, putting it to the power of the number of ways of taking a 2x2 block sample, which is the number of squares and length of the grid minus 1 squared, and subtracting from 1 again. This value represents a probability of obtaining at least one of such a sample of 4 squares, or one more rare, out of the whole population grid. In other words, it's the probability that any random population grid of this size has at least one of a 2x2 block sample of this probability. This calculated probability is always slightly higher than the parameter it estimates, as all of my simulations have shown. But it is never lower, and that is because the thing that causes the actual probability to be lower than the estimated probability, the overlapping sampling method, can by definition never cause the estimated probability to be lower than the actual probability. Simulations seem to indicate that this estimation is around, at most, 1.62 times the actual probability, and that the closer the given product is to 0, the closer to this ratio the calculated probability and actual probability become. Let's go back to the cancer example. Say there's a group of people in which we see abnormally high cancer rates. They're probably not clustered in an exact square shape, but if we make our grid with big enough squares, then no matter how we rotate or shift the grid, this cluster of people will always take up a 2x2 block of 4 adjacent squares. Say we overlay this grid onto the country these people are in. The sampling distribution is still expected to be normal, as we established when I first brought up the example, just like in the thought experiment. We're still sampling 2x2 blocks of squares, and there's still a very finite number of ways of sampling 2x2 blocks off a grid overlaid onto a country. The country's shape means that the number of ways of sampling probably differs very slightly based on rotation, but I'm sure that there's a way to be conservative with estimating that number. Thus, the only practical difference between my simulations and the real world is rotating and shifting of the grid, which doesn't change the calculated probability if the squares are large enough, and oddly shaped population territories, which again shouldn't result in an incorrect calculation if we estimate the sample number conservatively. Now I know what you're thinking. Just kidding, I actually don't. Probably something like, wow, this guy's a genius and very cool and talented and stuff. But I do know what I was thinking. Fantastic, we did it. It's literally done. Boom, easy clap. But then I realized something. I recalled some pertinent information which some of you might not be privy to yet. The Earth, you see, is a sphere. And unless you're sampling in the form of one of the platonic solids, this technique simply won't work in 3D. Or will it? If we have a 2D population, then regardless of the shape of the population, the number of ways of sampling a 2x2 block out of a grid overlaying it is relatively the same. So in 2 dimensions, the number of ways of sampling is correlated only to the surface area. This is purely intuitive, but maybe, just maybe, we can pretend the Earth is flat. Now hold on. We know the surface area, so maybe, regardless of how it's shaped in 3D space, there will still be the same number of ways of sampling the area. This may seem ridiculous, but consider the following. Imagine you have a piece of paper with a population on it. Now bend the paper. It's got a 3D shape now, hasn't it? But that shouldn't affect anything we're dealing with. Now, of course, a bent piece of paper can be bent back into 2D without distorting it, while a sphere section cannot. But, I don't know, it just seems right. I'll try to prove that we can just pretend the Earth is flat with a simulation or something in the future, hopefully sooner rather than later. Stay tuned.